Nicolas, je sais pas.
Ok.
Parce que c'est pas automatiquement, moi, Romain, il est sélectionné.
Avec le mail de convocation. Ouais.
Ok. Mais juste Romain, comme il n'était pas annoncé comme Theo,
Ah oui.
il m'a envoyé la réunion. Ouais, j'en ai fait la moitié, je lui ai envoyé la procuration, il vient de me l'envoyer signé.
Ok, bah parfait. De
toute
façon, moi j'en ai pas besoin, c'est après quand.
Signé pour que Rémi puisse signer à leur place.
Non, c'est moi qui vais signer à leur place, mais par contre, Rémi, il faudra quand il mettra le document de soutenance dans Adoum, il faudra qu'il mette les procurations avec. Pas qu'il fasse un PDF.
Ok, tu as bien pu partager ton écran.
Ah ouais, ce live, c'est bon.
Donc là, le live, il est bien
Et
lancé.
sur pas mon écran par contre. Là, sur Zoom.
Non. Attends. Oui, il y a que Théo.
Pourquoi?
Mais en fait, je sais pas dans quelle salle je suis. J'arrive pas à
Participer là. Ah, mais en fait, tu t'es pas mis dans une
salle de répartition.
Do all your questions.
All the questions, okay. And I start with so maybe I can start with you. You're okay?
Ok, c'est bon, on te voit bien, Théo, sur le YouTube.
Ok. Est-ce qu'on m'entend bien sur le live? Est-ce que tu peux juste checker si on m'entend bien sur le live? Le micro est bien. Juste checker si on m'entend bien.
So now we're waiting. He's coming. He told me where you start. 2 minutes before. We'll be there.
Just in time.
It's family stuff. Ah ouais. Yeah. C'était au Cameroun que ça. Mais avant de passer.
Non, c'est une fois. Quand tu mets dans la ligne.
Oui, bien sûr.
Quand tu mets dans la
ligne. Et je renverrai un scan de tous les trucs, dedans sur Adobe.
Ouais.
Et après, j'enverrai en papier. Là, je sais, chaque télé, là, ça marche pas. C'est génial. Je le fais demain. En gros, tu sais, je fasse une liste qui fasse chaque unité est valeur en cours, mais en gros, les qui sont sous-évaluées sur la liste. Tu vas optimiser la salle de valeur d'optimisation de la salle de valeur. C'est avec le jeu du sens pour les moyens. Le fléché, comme ça, ça va faire une situation de sort en meilleur, si tu veux, qui respecte les règles de tout. Je l'avais pas vu, ça, je l'ai pas. Mais quand on n'est pas parlé des slides, du coup, j'en ai dessus. Ça a commencé à expliquer. Slide one. I just think the typo. Okay, so I will say maybe on this because you guys have the wood. Next. C'est chiant.
Oui, c'est quand tu rapportes du souplesse, c'est très français
On va en anglais et on traduit en français.
Ouais. Oui, on va faire.
C'est bien de le faire.
Ouais.
Je
regarde, ouais, c'est ça. Qu'est-ce que tu fais là? Il y a rien qui te doit raconter. Il est bonne sortie de
Et vous? Pas porter dessus, donc
Ben,
juste que nous.
Non, mais moi, j'ai un peu de c'est juste là, tu vois.
Ça manque de petits. C'est là, toi? Bah non, mais je cherche un autre endroit, mais.
Non, non, non.
Ah ouais? Ah oui, ouais, t'as raison, ouais. Ah super, mais il n'y en a que sur le premier rang. Ok, ouais, très bien.
ils sont arrivés ou pas les...
Pas encore. Pas encore, pas encore.
C'est que... Romain?
Tu m'entends?
Non, du coup, j'ai pas le
Mince.
son.
Test, 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 test.
Attends. Ouais, vas-y, je t'entends, je pense là.
Est-ce que c'est bon? Tu m'entends quand je parle là?
Ouais, je t'entends surtout sur mon ordi. Je sais pas comment on frappe au niveau des questions,
Ok,
mais en tout cas, je t'entends là, ouais.
ok, super, cool.
Ah ouais, mais du coup, je sais pas comment on fera. Je sais pas, j'avais pas pensé à ça. Peut-être ça. Peut-être ça. J'avais pas réfléchi à ça.
Au pire, tu paraphraseras mes questions, puis...
Ouais, ouais, bah, on retestera après, mais je peux tester. Sans, tout le monde n'est pas là, donc je peux tester maintenant. Ouais, mais je peux tester. Pas tester. Ouais, de mon ordi, mais je sais pas, il y a un fil qui traîne. Il y a un fil qui traîne, moi je brancherais bien.
On va te confondre le max.
Ah, mais je peux peut-être sortir sur le. De qui? Ben, je viens de l'enlever le lien Zoom. Il n'est pas encore connecté. T'avais renvoyé. Et des détails, il n'y a pas vu ça.
Hello,
Ah, voilà, c'est bon.
Là.
Hello.
hello, hello. Ça
Ouais,
va, on m'entend bien?
ouais, on t'entend.
Bien.
Mais, ouais, et Rémi, on attend Alex. Ouais.
J'ai pas de news, ça veut dire qu'il est en train de marcher vite. J'arrive. J'ai un SMS. Théo, on a un endroit pour délibérer.
Mais après, on a une salle, on peut juste vous avez gardé une ordi.
Ouais, ouais, ben vous nous avez à la salle.
Et on est dans la salle, et vous verrez.
On prescrit. Et il y a un deuxième réseau aussi, ouais. C'est une bonne question. J'ai l'impression, je pense qu'il y a un deuxième réseau.
Un soir, en fait, on vous écrit une salle, on la communauté social. Là, vous pouvez vous mettre avec moi, je vais mettre dedans. Et
D'accord. Ouais, ouais, ouais. Non, sinon, on va faire un zoom à nous. On peut faire partie. Sinon, on va bien. C'est mieux que je jouer seul à avoir le. Je crois que je connais. Sorry. You seem to have done everything. Ouais, un peu obligé.
c'est bon, on est tous là. Okay.
Theo, are you ready?
Yes.
Ah.
C'est bon, juste.
Débranché. C'est OK?
Yeah.
Okay, so let's start. Welcome everybody. So we are here for the PhD defense of Theo Gnassounou.
Perfect. Right? Yeah, perfectly. Yeah.
Okay, great. And it was a PhD under the supervision of Alexandre Grandfort and Rémi Flammarion. And the jury is, I'm the president. It's an honor. Agnès Desaulneux. I'm from the Centre Borelli ENS Paris-Saclay. And we have Alain Rakoto. It's okay. I simplified. From Université de Rouen. We have also Martine DeVos from Leuven University, who are presenting. And online we have Romain Tavenard, professor at Université of Rennes, and Nicolas Thom, professor at Sorbonne University, but not in Sorbonne University.
Yes.
Okay, so we are listening to you for about 45 minutes.
Okay.
And then we'll have the questions.
Okay, perfect. So let's start. Okay, so hello everyone. So I'm very happy to be here today to present the work I did during these 3 years. So I want to thank all the jury to be there. And so my PhD is called Multi-Source Domain Adaptation for Learning on Biosignal. And so this presentation will have 3 parts. Each of these parts is represented by one color. So first I will introduce all the concepts that we will see during this presentation, focused mostly on domain adaptation. Then we'll have a part focused on a Python library that I implement for domain adaptation. And with this library, I did a benchmark for domain adaptation. And we find that if you want to apply correctly domain adaptation, you want to be specific for your data. And that's why we try to do on the third part, where we try to tackle the distribution shift for biosignals using optimal transport. So first, let's introduce what is domain adaptation. So just there is for the introduction, there is some box in French for people that not speak good English. So I think most of you are already use machine learning, so you can do a lot of things. So for example, if you want to classify pear and apple images, you can choose your favorite classifier. You will try to find the most discriminative features between these two images, for example, the color, the texture, the shape of your images, and then you will know if it's an apple or a pear. And then it's nice because you can give new images of pear and apples, and it will give you the right answer. But so you can be, okay, it's cool, I can deploy it, give it to new people, but if you're maybe one user can give quick draws of pear and apples. And here you cannot be sure that the classifier will give the right answer. And it's the same thing, for example, if you give paintings of pear and apples. Because here we still have the information on colors and texture, but it's not exactly giving the same information. So in domain adaptation, you will have different domains, for example, 3 domains. Each of these domains is describing the same thing. So we have pear and apple images. The first domain, we have real images with white background. The second one, we have just black lines, quick draws of pear and apples. And the last one, we have paintings. So they are not describing in the same way the pear and apple images. So we have what we call a distribution shift between our domains. And you can have this problem in different fields. So for example, if you want to learn a car to drive autonomously, if you learn it on clear images, you're not sure that it will work on when you want to drive in a fog or rain weather. And if we take an example maybe a bit closer to what we studied during this presentation, is medical imaging. So if you want to record something, for example, a functional MRI of different subjects, you will have different records, but each subject have a specific brain structure. So you cannot generalize between subjects because maybe the part that will be activated during the task will not exactly be the same. So especially for medical application, you want to trust your model. You want to be sure that if you learn something on one subject, it will work on other subjects. But when you have distribution shift, there is an impact. So if we take a simple example, so we want to classify dots. So we want to classify the blue and the red dots. In domain adaptation, we'll have two types of domains, one source domain and one target domain. You can see that there is a distribution shift between the two. So we have all the data from the target are shifted in the upper right part of the plots. But in domain adaptation, we'll suppose that we don't have access to the labels of the target domain. So we don't have the colors of the dots here. So if I ask anyone in this room to classify the dots, you will just draw a line just there. But if you're doing that and you try to predict on the target domain, you will misclassify half of the dots. And this is not something that you want. You want to be sure that there is no drop in performance when you train a classifier on the source domain and you test on the target domain. And in practice, you have different type of distribution shift. So the one we saw just before is the conditional shift. So everything is shifted, but you can have, for example, covariate shift, which means that the distribution of your data is different. So here, for example, we are more centered, but we still have the same probability of y knowing x. You can have also the target shift, which means that you have a different class proportion. So here you can see that we have more blue dots than red dots. And you can have a subspace assumption, which means that in the initial space, we have a shift, but we can find a subspace where there is no shift anymore. So for example, here, if we take this example, in source domain, if you are above the diagonal, you're blue. If you are under the diagonal, you're red. It is the inverse in the target domain. But if you project everything on the diagonal, you can see that if you are in the middle, you're blue. And if you are on the edges, you're red. And it's the same for the target domain. So, okay, we have different type of distribution shift. And you can use domain adaptation to tackle this shift. So to avoid this drop in performance when you train on the source and you test on the targets. And depending on the type of shift you have, you will use different type of methods. So if you have a covariate or target shift, you will use reweighting methods. So that will aim to put more weight on the source samples that are closer to the target samples. But you can use, if you have a problem of conditional shift, you use mapping method, as we try to project the source domain to the target domain. And for the subspace assumption, you can use dimension reduction to find this invariant subspace, or you can use deep learning methods that will try to find, when you learn your deep learning architectures, you will try to find the feature space that is invariant between domains, basically. Okay, so just for the next, we'll focus and give a little example for the conditional shift. So remember, we have source and target domain. So we don't have any labels, so any colors for the target domain. And so the goal is to find a map that will project the source data to the target data. And to do that, you have plenty of methods. You can use covariance mapping. You can use optimal transport that will aim to find this best transport map. But you can regularize this optimal transport and maybe use the entropic optimal transport. And here you add a new term. So you have the hyperparameters to tune. So remember that because it will be important for the next. So sometimes you have hyperparameters for your methods. Or you can use linear optimal transports that suppose that your distribution are Gaussian. So all of this method will be described more in details in the next. And so then when you have this transport map, you can transform your source data, and then you can learn a classifier on the transform source data, and you see that now it's working well. So we don't have anymore this drop in performance. Okay, so you can see there is a lot of things already done in domain adaptation. And so there is still some challenges that we try to tackle at least a bit during this PhD. So I had three main focus in this PhD. So the first one, when I studied my PhD, I look a bit to all the literature, and I see that there is for all this type of methods, you have plenty of methods already implemented, and it was hard to know which one we can use, etc. So the first thing that I did when I was reading all this paper, I studied to implement SCADA. SCADA is an open source domain adaptation library that makes easy to use the domain adaptation. So it was the first contribution I did. And then when I look a bit further at the paper, you see that they are not always applied to the same the same data sets, mostly computer vision, and also the validation procedure was not perfect. So most of them are not exactly saying how they validate the high performances of different of their methods. So you're not exactly, you don't really know how to validate the parameters. So it's the blue articles. Some of them are using the target labels, but remember, we suppose that we don't have access to these target labels. So it's not realistic. And you have some paper that propose good and realistic validation procedure that do not use any target labels. And so we said, okay, maybe we can try to compare all these methods with the right validation procedure on different modalities. And so we create SCADA bench, which is a benchmark for domain adaptation using SCADA. Okay, and then after this benchmark, we say, okay, maybe we need to be a bit specific to our data. And my data was electroencephalography, so EEG signals. So we focus on biosignals. So for EEG, you have different captors, different sensors put on the scalp of one subject, and you record the brain activity during one task. And you have various applications with EEG signals. For example, we'll focus mostly on sleep staging. So you want to classify the sleep during one night, but you can detect epilepsy. You can do brain computer interface that asks the subject to think about moving right or left hand, and you see which brain part is activated. And you have plenty of application. But in biosignals, you have also a lot of variability. So you have variability in the population. So if you take one data set, you will have different gender in your population. You will have different age. Maybe one patient can be healthy or diseased. You have also variability in devices. So remember, you have different sensors in the scalp, but you can have different number of sensors. Maybe the position can change a bit. And you have also variability in interpretation. So I think some of you have already have two diagnoses for one symptoms by expert. And it's the same thing. For example, this table is 5 different sleep experts that annotate the same dataset of sleep staging. And you can see that there are not the same scores, so they are not annotating in the same way. And there is always at least 20% of mistakes. So we have all this variability. So we have distribution shift. And remember, if we have distribution shift, we can have drop in performance. So even in biosignal, shift happens. And so to check that, we took different, at the beginning of my the study of biosignal, I took different dataset of sleep staging. I train on one dataset and test on another one. So there is shift between all these datasets, and you can see that there is a drop in performance when you train on one dataset and test on the other one. So we say, okay, there is domain adaptation that take out this shift. Maybe we can use these methods. That's why I try to do using different type of methods of domain adaptation. But you can see it's not working so well. So we are not improving the score except for J-dot. Okay, so the first things I did for biosignals during my PhD is to propose a new method called Monge mapping normalization based on optimal transport that try to tackle this shift. And then after proposing this method, I try to extend it in a two-way. So first one, I extend Monge mapping normalization for multi-channel settings. And I put some statistical guarantees in this paper. And then in the second time, incorporate Monge mapping normalization inside deep learning architectures to create PhD norm that normalize your data inside the network. Okay, so it was the two main focus of my PhD. So I will start from with SCADA and SCADA bench. Okay, so the first things I did was when I was reading all this paper of domain adaptation, I was always implementing the methods in a package, a Python package. Then we call it SCADA. And so SCADA has a homogeneous API for all these domain adaptation methods, both shallow and deep learning methods. And this API is escalon compatible, which means that you have an estimator with a .fit, .predict. You can use your estimator inside the pipeline, a grid search, So it's very easy to incorporate it in existing framework. And what is nice is you have the scorer. So this scorer will help to validate properly the hyperparameters without using any target labels. So just for a little example of SCADA, so in SCADA, we have a specific data format. So we'll have X and Y. So it's the things you use usually. So X is the features of your samples. Y is the labels of your samples. But you have a new parameters called sample domain, which will give for each of your samples in which domain you are. So if it will be positive if you're from source, it will be negative if you're from target. And this sample domain will help to mask the target labels during training. And then if you want to learn and to use domain adaptation, you can import from SCADA your favorite methods, for example, optimal transport mapping, and you can initialize it. But maybe you want to regularize it. You can use the entropic OT mapping, but remember, now we have parameters here, but you can use it if you want, and then you can just do a dot fit XY sample domain, and then you will adapt and then classify. And so it's very easy to use, but you can do plenty of other things, of course, with SCADA. But then, so you can see here, we have parameters to tune. So there is still the question of how can we tune these parameters. So remember, in our setup, we have source domain and target domain, but we don't have access to the labels of the target. So if you want to validate, the first solution can be, okay, maybe we can split the source data into training and validation set. But if you are doing that, you will learn a classifier and find the best parameters to adapt from the source to the source. But it's not something that you want. You want to adapt from the source to the target. So it's not a possibility. The second solution we can create a training set from the source and a validation set from the target, but it's not possible because we don't have access to these target labels. So some papers are doing that, but it's not realistic because it's not the setup that we want. Okay, so it's not a solution either. And some papers are proposing a right validation procedure like circular validation. So for circular validation, you will have a first classifier, and you will train it to adapt from the source to the target. And so you will use the source, the X and the Y from the source. And of course, you don't have any target labels for the target domain. Then when you train this classifier that adapt the source to the target, you can predict the target. You can predict some pseudo labels from the target. So now we have labels. Maybe they are not the true labels, maybe they're not the right one, but we still have some labels. So we can do the inverse. We can train a classifier to adapt from the target to the source. And then we have this new classifier that can adapt the target to the source, and we can predict new labels from the source. And now we have the true labels of the source, so we can compute the score and without using any target labels. So now we have a score, and we can validate our parameters. So you will see in the next, it's working pretty well, but the only drawback is that you need to train two classifiers. So if your classifier take a long time to train, it's hard to use it. Okay, so what do we have now? With SCADA, we have plenty of methods of domain adaptation. SCADA implement also some scorer to validate, to give good validation procedure. For example, circular validation, but you have different validation procedure that use no target labels, like reweighting methods or entropic minimization methods. And then we downloaded different modalities, so two computer vision modalities, two tabular data sets, two natural language processing data sets, and one biosignals, which is a BCI data set. And then we just missing one good framework to do this benchmark. So we use Benchmark. So it's allow us to implement the benchmark, and now it's very easy. If you go to SCADA, if you want to add a new method, add a new score, or add new modalities, it's very easy to do it because everything is public, and you have all the already computed score available. And so we did all these benchmarks, and then we got a lot of scores. So we have maybe a big table, a bit overwhelming, but I will try to do my best to explain it. So here we are looking at the score on the final target accuracy, so our final score. So we want to be the best. The two first line, we have the train source. We say that we train only on the source domain. So of course, it will not be the best because you remember if you train on the source, there will not be a good performance on the target. The second line is the best score you can have because you train on the target, only on the target. So you have no shift because it's target to target. And then you have all these domain adaptation methods. And if the cell is blue, it's meaning that if you use domain adaptation, it will help to increase the score. If the cell is red, it's meaning that you will decrease the score compared to the train source. And if it's right, it's doing statistically nothing. Okay, so it's still there is a lot of number, but what we can conclude of this table is that if we look at the left part, we apply all this method on simulated data sets. So we know the shift of these data sets. So remember, if we have one shift, we know that some method will work perfectly on that because they are designed for that. So if we focus on covariate and target shift, you can see that reweighting methods are the best methods. If we focus on conditional shifts, you can see that mapping methods are working well on them. And if you look at subspace assumption, we should have more blue here, but it's not working so well. But I think it's because our simulated data set is a bit hard to fix. And then if we look at all the real data set that we have, so all these modalities right there, there is a lot of red cells. So it's not really something that we want. You can see that Gaussian rewrite, for example, or TCA is not working at all on real data sets. So it's not working, but we have some methods, for example, linear optimal transport, that is working pretty well. So we have only blues and sometimes a bit of white. And why is it working? Is because there is no hyperparameters to tune. So we don't need validation procedure because we don't have parameters. So that's why I think we get the best result because it's very simple. So the simplest method is working the best. And I think if we validate properly the parameters, so if I use, for example, a supervised scorer on the target labels, the same table will have a lot more blue cells. And that's what we can see here. So we look at the comparison between the cross validation score for different scores. So the supervised one is the one where we use target labels. And then we have compared to the target accuracy, so the final accuracy. So you want a good correlation between the two. And you can see that for the supervised score, that is not realistic, we have a good correlation, of course, because we are using the same kind of labels. But if we're using domain adaptation scorer, you can see that the correlation is a bit worse. So for the three of them, there is no correlation at all. And for importance weighting scorer, we have okay-ish correlation between the two. But for serial validation that I presented before, we have a good correlation. And that's why it's the best one to use right now. But maybe for deep learning methods, not the best. Okay. So after that, so you can see that you have to know the shift, you have to know the parameters. So you have to be specific to your problem. And that's what we try to do on the last part of this presentation for biosignals. So remember, we focus on biosignals and mostly on sleep staging. So if you have, for example, sleep disorder or sleep apnea, if you want to know it, you can do you can record your brain activity using EEG signals for one entire night, and the sleep expert will annotate each 30 seconds of your sleep into one of the 5 different classes of sleep. So you have the wake, so you're awake. You have the REM, is the rapid eye movement, and then you have 3 degrees of sleep. And then using the shape of your signal and using the frequency, the sleep expert will annotate each 30 seconds, and then you will have this hypnogram that gives the evolution of the sleep during the night. And if you're sleeping well, you should have some cycles, and if you're sleeping badly, you will have jump between your stages. Okay, in our setup, we'll suppose that we have a multi-source domain adaptation problem. So we have different subjects. So we have source subjects. For example, this 4, 1. So remember, if the one domain is source, is because we have labels for this domain. And then you have a subject T that is different from the other subject and where we don't have any labels. So remember, we have variability, we have distribution shift between these subjects. So of course, if we train only on this subject and train on the subject T, we will have a drop in performance. So at the beginning, I was trying to know if we have variability, what are the consequences on the signal. So I tried different things, and at the end, I found that if you look at the power spectral density of your signals, so the PhD of the signals that represents the frequency activity of your signals, there is some shift between this PhD of different subjects. And so we say maybe you can try to align them. So the first thing we say, maybe you can align them to one common reference. So we need to find this reference. And then we want to know how to project them. And so we have to use that to find this reference and project all the PSD to this reference. We use optimal transport. So if you don't really know what is optimal transport, I will give you a little introduction with a very simple example. So imagine you are in Paris. There is, we'll consider two distributions, one source and one target. So the source distribution will be the red rectangles right there. So there are EG device factories. So for each one of these factories will supply different numbers of EG devices. So for example, for the factory D, you will have 15 EG devices to give. And then you have a target distribution, so the hospitals, the blue circles, and then this hospital will need EG devices. So for example, Lariboisière needs also 15 devices. And so this optimal transport will find the best way to transport all these devices with a minimal cost. So first we need to define a cost. So we can take the Euclidean distance. So here we can see that for between the E and Saint-Perrine, we have a high cost. Why? Because Saint-Perrine and E are very far. And for the C and Pitié-Salpêtrière, we have a low cost. Why? Because C and Pitié-Salpêtrière are very close. And then when you optimal transport, we find this map. So all this yellow arrow that will move the EG devices to the hospitals. For example, the D will move the 10 EG devices to Lariboisière and 5 EG devices to Saint-Louis. Okay, so you can formalize everything in mass, of course. So you have two distributions. Each one of these distribution is describing by the probability mass, so the supply and the need of devices, for example, and the location, so the location of the hospital and factories. And then with that, you can define the Wasserstein distance and the Monge mapping. So the Wasserstein distance is giving the minimal cost value to move everything, and the Monge mapping is giving how you want to move, for example, the devices from the factories to the hospitals. But here you have to optimize things. You have an optimization problem. So we simplify a bit our setup, and we suppose that we have Gaussian distribution. So now our distribution are described by the mean and the covariance of your distribution. And so you can still define a Wasserstein distance and a Monge mapping. But what is nice when you suppose that you have Gaussian distribution is that everything has a closed form. So now the Wasserstein distance is the Bure-Wasserstein metric, so estimated with the source and target covariance. And the Monge mapping is just a linear operation between a transport map A with the data X, and the transport map A is computed using also the source and the target covariance. So it's very easy to do. So now we know how to move one distribution to another one. And remember, we also want to know where we want to project everything. So we need to find a reference. So now we suppose that we have multiple Gaussian distribution. And this reference will be the Wasserstein barycenter between all these Gaussian distributions. So what is nice, if you take the distribution that is the closest to everyone in sense of Wasserstein distance, you will still have a Gaussian distribution. So your barycentric distribution will be defined by a mean and a covariance. But the only problem is that we don't have any closed form for the covariance sigma bar. And usually you can use an optimality condition like this fixed point algorithm to find your barycenter, so the covariance of your barycenter. Okay, so now we have the reference and the alignments methods. So we can propose the Monge mapping normalization. So here we suppose that we have different source distribution. And the first step will be to learn this barycenter. So we have three different distribution in the colored ellipses. And we learn this gray distribution that is the barycentric distribution. Then you can align all this source distribution to the barycenter, so like that. And then everything is aligned, so you can train a classifier to separate the color of the dots. And then at this time, you will have a new target distribution. So remember, we don't have the colors here of the dots. So you already have compute the barycenter and train a classifier. So you can project your target distribution to this barycenter, and then you can classify it using your train classifier. And it will work because everything is aligned. But for signal, it's not very doable. Why? Because still we need to compute the barycenter because we have an optimality condition. And in second, we use square root of covariances, but for signal, it can be very big covariances, so high computational cost. So we'll simplify again the computation, and we'll suppose that our signals are, so still Gaussian, of course. Now we center the signal. So we suppose that we have univariate signals. So here the sigma is not the spatial covariance that maybe you use. It's the autocovariance, so computed between time lagged. And then we suppose that our signal are stationary and periodic. So what is nice is now you have your signal, you can compute the covariance. And if you have these two assumptions of your signals, the structure of the covariance matrix will be totally circulant. So which means that the diagonal are the same and are repeated over time. And what is very nice with this structure is that you can diagonalize your covariance in the same basis. So here, the F will be exactly the same for all the totally circulant matrices. And there are the Fourier basis. And the diagonal, so your proper value will be the power spectral density of your signal, so the PSD. So now we have the covariance that is equivalent to the PSD. And so it's very nice because remember, we have two steps. So the first one, we want to compute the barycenter. And the second step is to map all our data, all our distribution to this barycenter. So remember, we have a optimality condition here, and we have a closed form there. But now we can diagonalize in the same Fourier basis all these covariances. So we can simplify everything. And when we simplify everything, we propose a new barycenter. So the barycenter PSD will be the sum of the square root of the element-wise square root of the PSD of each domain. And for the mapping, of course, we still have a closed form. But this closed form is even simpler because now we have a convolution operation between one filter H and the signal X. And the filter H is computed with the target and the source PSD. And so just as an illustration, imagine you have different PSD from different distributions or subject, for example, in green. You will learn this barycenter, this is the black dotted line, and then you can project all this PSD to the barycenter, so everything is aligned now. I just want to come back a bit on the assumption of the stationarity and the Gaussianity in our signals, because of course in real world, our signal will not be Gaussian or stationary. You can see it if you look at the distribution of the amplitude of your signals. It's not Gaussian. If you're looking at the running mean or the running NCD of your signal, it's moving over time, and it was sure because we have changing state in the EG, so of course it's not stationary. But all these assumptions are made to have effective learning. And I think the real assumption is that we suppose that most of the shift is comprised in the first order and the second order of the statistics. So we tackle most of the shift using that. So we keep some individual information that can help to classify after that. So in this first paper that we propose, we just do a very simple application on 3 different datasets of sleep staging. And so we have only 200 subjects. And we use a simple convolutional neural network architectures. And we focus on universal signals. And so it was very simple, but we get good results for any pairwise adaptation. We improve the score using Monge mapping normalization. But it was a proof of concept. So we wanted to go a bit further with this method. And that's why we extend it in a two-way. So first, we use it for multi-channel settings. So in this paper, we propose, instead of using PSD, to use cross-PSDs to capture the spatial information that is, for example, very important for BCI application. And in this paper, we also give a lot of statistical warranties on the estimations. And then we wanted to go beyond this pre-processing step with PSD norm. And so PSD norm is a new normalization layer that you can, like that, with that, you can align between, inside your architecture at different layers, you can align your data. And with this PSD norm, we apply it on with the SOTA architectures and more data. And just for the next and for the last part, I will focus mostly on PSD norm paper. So let's move to the last part. So first, we apply it. We use a UNet architecture proposed by Perslev et al. So this architecture is made using encoder blocks and decoder blocks. And what is nice is that as input, you can give any length of sequence of sleep. So for example, you can give 70 minutes of sleep, and at the end, you have a segment classifier that will give one adaptation every 30 seconds. And the question was, okay, we have these better architectures. How can we use Monge mapping normalization inside this layer? So we inspired from the classical normalization in deep learning. So for example, the batch normalization that will learn statistic and align over the batches. So we learn the mean and the variance. We have the instance norm that learn the statistic only over one signal from the batch. And you learn mean and variance. And so we inspire from instance norm because we learn statistic only from the signal here, but we learn not only the variance, but we learn the covariance, which is equivalent to the PSD now with this Fourier transform. And so as we done it for Monge mapping normalization, we need a barycenter. So this barycenter will learn, will be updated with a geodesic update for every batch. And then we can learn this filtered that we have before, computed from the targets and the source PSD, basically. And then we can convolute it to the batches. And now, for all the signal of our batches, we have aligned PSDs. And then we remember we have only 3 datasets before, but now we have 10 datasets for this paper, and we have more than 10,000 of subjects. So of course we have better results because we have a better architectures, a higher number of subjects. Of course, the score are better. So it's the last big table of this talk, and so here on the upper part we train our units on all the subjects, and on the lower part we train only on 10 times less data as the upper part. And so we compared PSD norm to 2 classical normalizations, so the batch norm and the instance norm, and we compare it also with the pre-processing method that we proposed before. And as you can see, PSD norm gives a more robust score to tackle the shifts, but it's also a bit smaller as before because, of course, we have more subjects, we have more variability in the training data sets, so we have less things to improve. But what is nice, I think, is that if you compare the score with PSD norm trained on only 10 times less data, we have the same score when you train on all the data sets with batch norm. So using PSD norm, you don't need as much as data as before. So it's also nice. Okay, so we come at the end of this presentation. So just as a remember of this presentation, so during my PhD, I first proposed SCADA that makes easy to use domain adaptation. Then with SCADA, I proposed a realistic benchmark that showed the limit of domain adaptation field. So you have to know the shift, you have to validate your parameters, and I think it's the bottleneck of domain adaptation today. And so you need to specifically design your domain adaptation method for each application. That's what I try to do for biosignals. So you see that distribution shift is a major challenge in biosignals application. And we propose Monge mapping that help to mitigate this shift for EEG signals. I think in PhD norm we saw, then I extended using multivariate signals, and we give some new theoretical guarantees. In PhD norm, I improve and increase the number of subjects. So we saw also that the more you have the data, of course, you will be more robust to the shifts. But still, with PhD norm, you can achieve good results with a limited number of data. So what is nice. Okay. And also during my PhD, I contribute to the open source. So of course, I contribute to SCADA Bench, but I also contribute to Brandycode and POT. Brandycode is a deep learning Python library for EEG decoding, and POT is a Python optimal transport library. And so I think for the next, there is still plenty of things to do. First, for general domain adaptation challenges, I think detecting the shifts can be very helpful. And proposing a more robust domain adaptation scorer can help a lot to validate properly and realistically your parameters. And I think something I want to do is also to extend SCADA and SCADA Bench to deep learning framework, because right now we are not the best for deep learning, but I think there is a big part of domain adaptation that focus on deep learning that I want to contribute. And then for domain adaptation for biosignals, we apply PhD norm and Monge mapping normalization only on sleep staging and a bit on PCI. But I want to know if we can use this method maybe on ECG classification or maybe any time series problem. And I'm curious to maybe compare domain adaptation with foundation models for biosignals, because now it's trendy and maybe you can do something. And just a general outlook of my PhD. So, of course, I learn things about biosignals and domain adaptation, but I also understand that machine learning has a non-negligible impact on society and environments. So, for example, just the paper of PhD norm has emitted 0.4 tons of CO2 just for the training. And so just as a comparison, Paris to New York is 1 ton of CO2. At least I didn't be accepted to NeurIPS, so I didn't choose the plane to go. And so I'm not against machine learning, of course, because I'm working on it. But I think we need to work better, like just to understand our problem, because maybe we don't need bigger models, we don't need biggest data sets. We can maybe just do a linear regression sometimes, and that can work also. And I learned also during this PhD that we have to design the experiments and maybe not launch a random experiment that use a lot of CO2 too. And so you have to design your experiment to not to avoid unnecessary computation. And I think doing open science can help you to do that, because you can learn how to code with others. You can share your code and data, of course, to collaborate, but also collaborating to open source package like SCADA, Brandycode, or POT, or anything is very helpful, because you will learn something and you will contribute to the machine learning community. And that's it for me, so thank you.
So now we have the questions, and maybe we start with people online, and we start with the reviewers. So Nicolas, if you can hear us.
Yes, I can. Can you hear me well?
Yeah, very well.
Okay, excellent. So thank you, Theo, for the invitation, and thank you to your supervisors for inviting me in reviewing this PhD. So I was very pleased to read your manuscript, which was very clear. I really appreciated reading it. And thank you. Congratulations also for the presentation today, which I think was very clear. So you had a very nice illustration that enable me at least to better grasp some part of your work. So congratulations for all that. So I am a question at several levels. So I will start by a question about. So I essentially have technical question about the Monge mapping method that you developed.
Okay.
First of all, I had a question about, so I think that's something that I wrote in my report. I had a question about the filter size that you use. So in the temporal normalization that you use, so at the end, it turns out to be a convolution operation, and then you have this hyperparameter on the filter size. And then you discuss the trade-off that this filter size can bring you in terms of distribution alignment versus class discriminability. And I would like to have your feeling on first on the impact of this parameter and how you can set up it in an automatic way, if possible.
So it depends, I think, of the application. When we did the first paper, so we have longer signals because we took one entire night to preprocess our signals. So here, it was not very sensible to these parameters because we in the paper we did sensitive analysis, and we saw that we show that taking different size, it gives good results, because I think the length was so long that it was not so important. But when we did the PhD norm, it was a question, because now we have so we took 17 minutes of sleep and not 8 hours now. So we took a very smaller filter size, and now it was more sensible to these parameters. So we tried, at the end, we just find that using PhD norm with different number of filter size was helping always compared to other normalization layer, but you can get, of course, better results when you use the right filter size. But we didn't validate it using domain adaptation scorer, for example. I think it's maybe a problem of PhD norm right now, because we don't validate it in a proper way. But I think we can use, and we should have tried also to validate with a good validation procedure, but we didn't have time to do it.
Okay. And when you say that, so in the first example, when you say you have very long temporal signals, and the impact of this hyperparameter is not that important. I was wondering if you explore that more in depth, just to check out if the alignment was okay, or was okay whatever the filter size that you have, or the class discriminability was still present. Do you have some insights on that? Because you have this trade-off between the two. Yeah.
We didn't study too much this threshold of do we have still do we kill all the discriminated features or not. I think we just saw that at a certain point we have a plateau for this filter size, so say we don't need to take a bigger filter size. But yeah, we didn't check this threshold and what is the impact.
Okay. And would you, for example, just to go ahead in that direction, I was wondering if so you are mentioning about using scorers, but I was just wondering if it can be possible to use the performance that you get on the source domain as an indicator of the class discriminity that you have, and just as a way to cross-validate the filter size that you have. For example, intuitively, if you decrease the filter size, you may no, sorry, if you increase the filter size, you may filter out some class discriminating information, right? And then maybe you can use the performance that you get on the source domain as a proxy to assess your filter size. What do you think of that?
it's still like the problem of if you have a bigger shift between your targets and your source. I think what is nice is that depending of what you consider as domain, you can still split with different subjects as source, and so you can still try to find the best parameters on a subsample of subjects in source. And I think it could work because what we saw with PhD norm is that we don't have a so big shift between all our datasets. I think only the SHA dataset was very hard to work on, but I think all other datasets, since you have plenty of subjects, the shift is not so big, so maybe we can do something like that and validate on the source.
Yeah.
And I think we didn't do it because it's also taking a long time. So having these big tables took us a lot of computation, but I think that's why also we didn't validate properly the parameters.
Yeah, so here you are talking about PSD norm. So I was just my question at the beginning was more general. It may also involve the previous chapter where you only align the input distribution. But, yeah. Okay. Anyway, thank you for answer. So now for PSD norm, so I think that's a very nice extension of what you did initially. So if I remember well, then when you learn your model, you limit to temporal correlation because you have this closed form expression that can be you can cast the barycenter as a convolution. Okay. And then how would it be possible to extend that to model spatial correlation as well? How would you approach that?
I think it's possible. You can do it even with the code we have. It's just that for sleep setting, you don't need it because the spatial information is not very crucial for classification. And just if you add the spatial information, you will have no more closed form for the barycenter, and you will take more time to compute the alignments also. So since we were applying only on sleep staging, we wanted to have the fastest PSD norm. And I think if we're doing the spatial correlation application, we'll have to maybe think about the computational time of this normalization layer. And I think it's possible, but we need to try it and maybe make some simplification in the code, maybe to go a bit faster. But I think I tried a bit because I wanted to try on images, but the application I did was not working very well. But I tried a bit to do this 2D because it's very simple, just to have our code working on for images and spatiotemporal problem is doable.
Yeah. And even in EEG, in BCI application, where your spatial correlation, channel correlation might be important. So I was wondering, to my understanding, your PSD norm approach, which is done online during training, is compatible with the pre-processing that you propose in the previous chapter. So I was wondering, just practically speaking, if you think it can be interesting just to combine, in some cases where you need spatiotemporal alignment, to combine a pre-processing based on this channel alignment, and then use PSD norm for temporal correlation. So maybe it can be a simple baseline. Do you think practically in the data that you have been looking at, it can be interesting to do that? What is your take?
Yeah, I think for sleep staging, I think it's not useful to do a pre-processing step. But if you're doing BCI, and that's what we saw in the paper where we do the cross PSDs, is that if you align only temporally your signals, you're not tackle the shift so much, and you need this at least to tackle spatially, or you will have better performance if you do the spatiotemporal alignments. So if you're using only PSD norm, I think if you want to use PSD norm for BCI, adding a preprocessing step using the Monge mapping normalization that we propose with cross PSDs, with the spatiotemporal alignments, will definitely help, because you will, yeah, I think it's doable, and but for sleep staging, it's not useful.
Yeah. But for BCI, you didn't experiment that yet. Just
Yeah.
you think it can help. Okay. And in cases, just to finish on that point, in cases maybe where you need a more online spatio-temporal adaptation, how would you approach that? For example, would it be possible, because here the computational cost for estimating the barycenter may be bottleneck for doing that during training. So what would you recommend if you would to make that practical?
If you want to apply it, yeah, with spatiotemporal alignments, I think what we did in the paper, we just do one step of fixed point algorithm, because I think it was enough to get a good reference where to project our signal, because that's what we showed that also in the first paper, if I'm not wrong, that you can take any type of references, but just the barycenter is the more robust, so you're sure that if you take the barycenter you will get good results, but you can use just a constant for the PSD or anything, and you can align to that and you will get good results. But just sometimes it was not working, but most of the time it was. But just using the barycenter is working always, so that's why we use that. But for the spatial temporal elements, I think just doing one step of barycenter, and you will get good references that will work for your alignments.
Okay. Thank you. Maybe I have a bit more time. So just to come back to the filter size, I had another question. I was curious just to have your feedback on that. So I came back to this filter size choice. So I was curious, maybe more from a theoretical point of view, if you can have some ways to quantify this trade-off that I was what I was talking about. So the trade-off between the class discriminability and the alignment between source domains. Do you have some ways to quantify that? I mean, depending, can we say something? So depending on the filter size, what is the loss that I have in alignment if I decrease it, and what may be the loss in class discriminability if I increase it? Maybe based on some assumption of your data distribution. I don't know. What is your opinion on that?
So your threshold will be between the alignments and the score.
And the class discriminability, I think that's the trade-off that you point out in your work. That's always the same trade-off, but which I think makes sense.
Yeah, it's a good question, because I think measuring the class discriminancy maybe is the things that maybe can be hard to measure, because it's still the same question. If you can detect the type of shift, you can know how much your two datasets are different. It can help a lot, of course, to know that. But just like that, I don't really know how to do it. We tried at the beginning to measure the difference between our two datasets, or between two subjects, just to find if there is a correlation between, for example, the Warshausen distance between two subjects and the accuracy, the final accuracy, and the drop in performance. But it was not correlated. So I think it's a bit hard to measure these things. So find, using that, the best parameters and the best filter size, I think is a bit hard, but maybe it can work. But you need to find the best score to know the difference between two datasets or two subjects, and like that I don't see how you can do it properly.
Yeah, I see. So maybe I was at this level. I was not talking on having an off-the-shelf solution to solve the problem, but still to be able to quantify the trade-off that we can have between these two objectives. But I see. I understand that is not that simple.
Yeah.
Okay, so maybe a bit more question about the assumption that you made. So
Yes.
to make your approach tractable, so you made assumption at several levels, which okay, and I think you really nicely point out why at least with in your benchmark it's relevant, or linear OT might be a strong baseline. So you have this Gaussian assumption, then you make further assumption on stationarity to derive your closed form solution for temporal correlation. So I was wondering, what do you think on the impact of those assumptions on the actual performance of your method?
I think it's not, you don't have a lot of impact, because we also check if there is a correlation between the Gaussianity of our signals and the score, and we didn't find anything. So it was working. It was working well if you are Gaussian or not Gaussian for our signals. And so I think just we suppose that we tackle most of the shift using that, as you can do, for example, for a batch normalization, you will just normalize the mean and the variance, but you will not normalize always like the higher order. And I think that's what we are doing that. And I think that's also why it's working, because we're aligning, but not too much. We are using the covariances, but we don't want to align too much. I think if you use the perfect optimal transport, it will be very long, and also I think you will break too much maybe your data. And using that, you just suppose that you tackle just the shift you want, and that's it. And so I think you can have Gaussian or not Gaussian signals, and it will work the same. But yeah, we didn't. Maybe with the toy datasets, we can check if we take a Gaussian toy dataset and a non-Gaussian one, check if we have the same results. But we have to design it. But
okay. And for example, for sleep staging, where you said that you have very long temporal signal, so here with your temporal alignment, you assume that the signal is stationary. So I was wondering if it could be interesting to try to align the signal more locally, just
more locally.
To which extent this stationarity assumption is problematic or not in this application.
But yeah, in PhD norm we align more locally, but I don't know if it's because it's more locally than 70 minutes, or
So what do you mean locally? I was meaning locally in the temporal domain, right? So yeah, because you mean because of the filter size, maybe. So can you?
Yeah, it depends. Yeah, just what we did for the first paper is that we took the PSD of all the night. So we have I don't remember how much samples, but it's 8 hours of sleep. So it's a big signal, and we learned this PSD. And so yeah, it's very global, and we incorporate all the classes of the sleep. And for and I think you want to have a global information, because if you're taking, for example, I think more locally, if you're taking, for example, one window and you align everything on the barycenter, I would be maybe afraid to remove maybe the class information. It's the same thing. It's a good question if you want, for example, to do hash prediction on your EEG, and you align. If you're doing our method, I don't know if everyone will have the same age. We just it depends what you're using. So more locally, I'm a bit afraid to remove too much information that is class discriminative. But it's a good question just to do it more locally.
Okay. Maybe you can, I don't know, enhance the model or use also local temporally localized barycenter. I don't know, just to make.
Yeah, maybe.
Yeah. Okay. Thank you. So maybe I will finish by more general questions. So I think at the end of your manuscript and here also at the end of the presentation today, you were talking about foundational models, so which have been successful in various data, so in NLP and vision in particular. And I wanted just to have your take on that, because of course I don't know the specific attempts or preliminary results that have been obtained for EEG or BCI application in general. So can you just elaborate a bit on where do you think we are at the moment on the capacity of those models to generalize across domains, across subject, across sensor, and what is the place for domain adaptation nowadays?
Yeah, so I didn't I look a bit to these foundation models. So it's a bit hard because you have different levels of foundation model. You have one for time series, you have one for EEG signals, and sometimes only for sleep staging. But I think not. I think the foundation model for EEG signals are often applied to one or maybe two data sets of sleep staging. You never apply it to several dataset like the units that we saw before our paper. So it's really focused on one or two sleep staging datasets. So I never really compared to the simple non-foundational models. And so yeah, that's why. And when I wanted to try a bit, it's not often easy to apply. Sometimes like big foundation models, sometimes it's a bit hard. But I'm trying to see uh, uh, if we can use foundation models. Just like my question first is just to see if we have good result on sleep staging, and then maybe we can use the maybe domain adaptation for the fine-tuning state to be more robust, but we're not exactly in the same setup because we suppose that we have some labels for the new data sets. So we're not in a domain adaptation setup, but more in a semi-supervised domain adaptation setup. So I don't know if we can exactly do the same, but just for example, in Scala you have plenty of shallow methods, and maybe if you have a good representation using this foundation model, you can maybe just use the alignments in the embedding space. It can tackle the shifts and give more robust accuracy. It's something that I want to try. Just instead of using all the deep learning domain adaptation methods that's refine-tune your architectures using different losses that sometimes can break a bit the things and you need to retrain everything. Maybe using for example, linear optimal transport just at the end of the embedding of the future X factor of your foundation model. Maybe you can have good result, and then you can train your linear regression or random forest and can give good results. And it's something that we want to do since a long time, and I didn't have time to do it, but maybe it can be full and very easy to do.
Okay. Thank you. I see that it echoes one question I had also in my report, stating that in PSD norm, when you assume that you have this Gaussian distribution, I think that so you can apply PSD norm at several layers of your model, and then intuitively when you train a model, the Gaussianity assumption, it becomes intuitively, or at least on the source domain, more and more fulfilled when you go up in the hierarchy, because your distribution becomes naturally more and more Gaussian. What is your opinion on that?
That's why we didn't put too much for PSD norm. We put only 3 layers of PSD norm at the beginning of the unit, and then we suppose that we don't have any more shift. So I think the first layer are incorporating some shifts in the architectures. So we need the PSD norm at the beginning, and then we stop using it because it's not you don't add so many computational time, but still a bit. And I think it's we do nothing. But I think it's the best. Just we align at the beginning, and then we stop aligning. This is just for the first level because I think after it's okay.
Okay. Okay. I think the time is a bit running out, so I will stop there. I have still a lot of questions, but I will give the floor back to the president. So thank you for all your answer, and congrats again for all the very nice work that you did. Thank you very much.
Thank you. So now we have the second reviewers. Martin Devet.
Thank you very much for the nice work and very nice presentation, also very clear. One of my students was following your work, and sometimes you answered my questions to her, so that's definitely a very good thing when you read it. But also been going in the discussion you had with the previous reviewer. For me, I think I'm not going. So although I like a lot the domain adaptation, I think the totally different way tackling it is exploiting diversity. And so, and that's going into the foundational model, and we can argue, like, do you need even alignment in a foundational model? Because if it's seen enough of variability, it will learn the representations. And going into the multiple data sets, we haven't published it, but we try just to train one model. It doesn't matter which one on a big data set.
Yeah.
And then when we see, like, you do a different data set, it starts breaking down. But what we did is then, okay, we have this few small data sets, and we just fine tune it with multiple small data sets, and we do better on other data sets than if you trained on these other data sets. So you basically generalize better by exploiting diversity than to really think about, okay, how do the domains align? And so for me, those are two very different approaches to the same problem. And I wanted to hear your perspective. Like, do we really need to try to align everything, or do we just have to try to exploit the variability we observe?
I think for sure the best if you use all the variability you have, and you can have it for your training sets. I think it will be better. You can see it on these results because we have less things to tackle because we have more variability, more subjects. So of course it's working better. But the question is more like, I think, can we have always this variability in our training set? And maybe we can still have a new data set that is very different. And when we tried with foundation model and to have this good representation, it was working most of the time on SIP staging, but for some dataset was not working so good because I think there is sometimes a very different one. For example, the chat dataset is very different because it's only child, so only children in this dataset. So it was the hardest one, and it was hard to have good prediction. So when you use batch normalization, it's not working so well. But then using our boss normalization is better. And I think maybe it's the one where I think just you not be sure that it will not change too much. I think everything is evolving, so maybe you will find a very different data sets. But I think it's always the same question. If you know your problem, you can know if there is a big shift or not. And
it brings me to another question, which is very general, but throughout the thesis, you pick what suits you, I think. And the question is, what is your domain?
Like our domain?
Your domain, because you have here your 70 minutes, you have one subject, you have one data set.
It depends of the paper, I think. For the first paper, my domain was the one subject because we have several subjects, and I learned the barycenter. So for me, one domain was more one subject because I took all the PhD of all the subject, and then I take the barycenter. So here, one domain was one subject, but hierarchical domain adaptation because we have like the data sets, then the subject, and then I just take the level of subject. And in PhD norm, the question is harder because now the PhD is taking from 70 minutes of sleep, and I learn this PhD, I align this PhD, so I can say, okay, maybe the domain is this small sequences of sleep. If I take like, yeah, I'm just doing the if I'm doing the same as the paper before, just one subject in PhD norm will be just one small sequence of sleep. So it depends. I think we have more hierarchical domains, so we have data sets than subject. Then
how do you, like, what is your advice? That's more my question. Like, what is your advice to treat data set like domain variability just because you have all the levels? Do you pick and choose for different applications, but it's not always clear. Also, to me, like, when is a subject out of domain? Definitely, if you keep in mind your first table, or you show like some domain adaptation destroys variability.
Yeah.
Sorry, destroys performance. So if your advice was just go to the smallest level, when it works well out of the box, you don't need to do domain adaptation. You can only ruin it.
Yeah,
so
I think
that's my question a bit, like, do you have any advice?
How to use domain adaptation?
Yeah,
like,
yeah, how to yeah.
Yeah.
Definitely in EEG. Let's just talk about EEG.
Yeah, because I think yeah, with this benchmark, it's hard to know if domain adaptation can really help. And for EEG, when I applied the domain adaptation deep learning methods at the beginning, it was not working on sleep staging because you're trying to find this feature invariance. I think it's not working. It was not working so well. And what we try to do is to understand where comes the shift in our data. And that's why we look at. I show the PhDs, but first we did different study of the class proportion, etc., and to know where is the shift and where we can try to maybe remove the shift. And for the PhD, we saw that it was working. That's why I think you need to understand your data. You need to go a bit to understand what is happening, because you cannot just use the methods and say, okay, it will work, because if you don't really understand what is happening, you cannot tackle the shift, or maybe use it, because maybe using the shift can be also useful, using this variability, as you said.
Okay. Going back to the spatial temporal alignment. So
Yes.
you clearly, I mean, I think mind mapping works nicely for aligning the PhDs.
Yeah.
You compare it also to Riemannian, obviously.
Yeah.
But then I even wonder, like, is there conceptually a big difference between how you align the covariance matrices?
No, if you just like the part is just you want to. Sorry.
Yeah. I also wanted to say, so you can answer this, but then my real question is, if you do have, like if you think about the EEG and you have topographies which represent specific frequencies, you start having interactions between the spatial temporal domains, and it becomes very hard to align, I think. But again, you're the expert here. So what I think, if like, is there an advice to always spatial temporal decomposition, or can you just do first spatial and then temporal alignment, and will it give you similar results or not?
Doing you need to try to do one step then the other one. To always do this all the alignment at the same time.
But is it disentangling time and frequency as you would like to do it, or?
I think yeah, there is still like correlation between the two. So maybe doing everything at the same time can help. But I think it's hard to know because the two applications we did is for sleep staging and BCI. I think each of these applications need either temporal information or maybe special. I think in sleep staging, I have often two channels, so the spatial information was not so big. So
I'm thinking, for example, in meditation, where you have both lower frequencies and higher frequencies and spatial patterns in different people, there is much more variability. Then the question becomes like you want to align the spectra, but sometimes you see that their totally wrongly aligned.
Okay. That's a good question. Like that, I don't see exactly what, well, like, I don't have the intuition what will be the best to do, and
But maybe a very practical question on the PhD norm. So you said in the unit you use it in the 3 first layers.
Yeah.
And do you still keep the bachelor layers afterwards?
Yeah, after we keep the bachelor layers.
And why?
Just, I think it was more like from at the beginning, just to not be too long to train, because it's hiding a bit of time, and you have I will say, I think you have around 25 normalization layers. We didn't want to put too much to add too much time to it. And then we try a bit where there is also like, and then we say maybe we can do a sensitive analysis of the depths we put PSD norm, and we saw that if you put more after, you just have the same results. So maybe we just tackle the shift at a certain point. We don't need more because it's already aligned, so we don't.
Yeah, but when I was reading it, I wasn't clear in which layers you did, but I was also thinking you can do it in the first layers because there the intuition about aligning spectra makes sense. Yeah. But the deeper you're in the network, the notion with spectra is probably also lost quite a bit.
Yeah, I think, and I think that's why also it was not. I think it was not helping anymore, like, because I think you have, aligning the temporal information after is not very useful, I think, at the end. And so it's enough just to align like but it's still I think it's still helpful because compared to the pre-processing step, you have better results, but I think it's because you can align a bit more, but at a certain point after it's not useful anymore.
Yeah. Maybe questions. Yeah, maybe you say it doesn't work on imaging, but to also add to the previous one. But how can we know? Because you always argue you need domain knowledge. But the practice is we try something. If it doesn't work, we try something else, and we then sell it as we have domain knowledge. But is there a way to when you start with a problem, like start thinking what are the properties, and definitely in terms of this non-Gaussianity, that it might have a detrimental influence or not?
Yeah, when I see it was not working for images, I just try. It was very brief, and just we didn't have so much time because.
No, but I fully understand, but
yeah,
I'm just thinking like this takes a year of work, and then you show this is it. But if I'm a user of your method, I just want a data set and I want to train it a week and trust it.
Yeah.
Right. So that's the difference always that we not between what we how we sell it and really if we can connect properties and definitely I think about images they're way more complex. So where is the simplicity versus the complexity that needs to be captured?
I think I'm not I don't really know like image processing perfectly, but with some discussion, what I understand is just using Fourier transformation for images not always the best things to do. I think I'm not doing these things in image processing, or more doing wavelet or things like that. I'm not sure because, but I think it's because I was talking with someone and talking to them like Fourier transform. If you use Fourier transform images, you will change the images too much, and maybe also is why it was not working so well. But maybe inside, I think the pre-processing step maybe will not work, but maybe inside the architectures, it can be more useful because since you do a new representation of your images, maybe you can help better inside the architectures.
Maybe a very final question to end is I like your theoretical bounds to derive, but I wonder like how practically relevant are they? Are they loose? Are they tight? Do they have any?
Ah. Yes, we didn't really think too much about it, but yeah.
Thank you very much.
Okay, so now we have maybe the question from Romain Tavenard. Romain, if you can hear us.
Yeah, thank you. So before starting with my questions, I would like to really thank you, Theo, for the very nice presentation you gave today and the very nice manuscript you sent us. I really believe that, for example, chapter 1 is like a marvel. I mean, it's so nice to read and really well explained, well illustrated, etc. So really thank you very much for that. And I think that was also the case of your presentation today.
Thank you.
So now I'm moving to the question part. Maybe I will start with rather technical questions. So you have this strategy in which you first compute a barycenter between your source domains, and then you will map everything to this barycenter.
Yeah. Yes.
My question is, do we have to align everyone to the barycenter, or could we pick another reference distribution? And what would that change if we did things this other way?
Yeah, we tried for the first paper to apply it to different references, and we did for a constant PhD, and then we did for Polo, and it was working. It was working not so bad, and just I think for some adaptation, so it was only pairwise adaptation at the beginning. And for some of them, it was not working very well. So I think one or two. It was always the same. I don't remember which one. And so just using the barycenter, I think it will give you a more robust reference. But I think you can use something else. And that's why for the spatial temporal alignment, for example, using only one step of fixed point algorithm, it will give you good score because you don't need, like, the barycenter is not crucial for our method. You just like you are sure that it will work with the barycenter, and maybe you can find other target or other reference, but just we have one that is working and it's fast to compute, and you're sure it will work always. So that's why we choose it.
Okay, and I don't know, do you have like any intuition why this is a good idea, or is it just fast to compute and it works, so don't look further?
I think just like you find I think maybe like just the jump between all the PhD will be the smallest possible because it's the one closer to everyone. So if you take, for example, you can choose, for example, you want to align to only one subject, but maybe there is some subject that are very far. Maybe it's harder like, to adapt them between each other. So maybe I think just because it's the closer to everyone, maybe it's the best way to do it.
Okay, thank you. Then you rely on the Gaussian assumption such that you can have these very efficient computations. You clearly introduce in your manuscript that there are other ways to do efficient optimal transport, I think. Why is the optimal transport between Gaussians a very good tool here? And have you tried other ways to make the optimal transport computations faster? And yeah, can you develop on that?
I think there is two things. I think it's just yeah, doing Gaussian transport. It's more effective because it's very fast to compute since you have your closed form, and then with the stationarity and periodicity assumption, it's even faster. So I think it's the first point, just to have effective learning. You have a second point, I think, that we saw in the benchmark of the mail adaptation is that if you use other optimal transport, it was not working so well. And I think it's because the transport alignments may be a bit more complex, and sometimes you have parameters to deal with. So like that, you remove all the parameters for your method. So it's easier to tune. And I think if you do the perfect optimal transport, it will be longer, of course, and maybe you will have to tune the parameters, but also maybe you will align too many things. And maybe just Gaussian distribution is why it's working well, because it's very simple, and you're aligned a bit, still like the first and the second order statistic, and that's it. Not changing too much your parameters, and not destroying too much information, but still, it's we didn't check that exactly. But maybe one nice thing to do is to check how much you can change your signals if you're doing Gaussian alignment or optimal transport. It's not something that we did.
Thank you. In your conclusion, I think, and also in your answer to the previous questions, one important point seems to be the ability to assess the kind of shift between domains that we are facing, its magnitude and the kind of shift. Is there literature on this topic? If there is, do you plan to have such diagnostic tools included in SCADA? And yeah, what do you think about that?
Can you just repeat the...
Yeah. My question is about assessing the kind of shift you have between your domains.
Yeah.
What tools exist for that, and are they really practical, and do you plan to include such tools in SCADA?
Yeah, I think I never read too much this kind of paper, so I want to do it, and and try it, and maybe incorporate it to SCADA. It can be useful, because I think if you know the shift, maybe you can apply the right domain adaptation methods. So having maybe just a tool that you just put your two domains and get the shift at proposing you maybe the good methods to use can be helpful. So yeah, I never try to do it right now, but I think it's definitely something that that's something I want to do in the next year.
Okay. And maybe my final question, just as Nicolas, I think I was a bit, I don't know, intrigued by your point on foundation models in your perspective. So I would like to ask, well, you seem to be, I don't know how to say that, but a bit suspicious about the effectiveness of these methods. So maybe my question would be, would that deserve a benchmark too?
Yeah, do a benchmark, yeah, compared to foundation model and domain adaptation. Yeah, I think I'm just like, it's just a question. Like I'm suspicious about foundation model and also domain adaptation. Just I think we have to compare compare fairly, just to know what is the best, even like for sleep staging, for example, even without talking on domain adaptation. It's just something I want to do, and I'm trying to do right now, just to know a bit how it's working, what are the results, can we improve them, and then if it's working or not, because it was for I think just the one shot was not working so well, so that's why I was saying maybe using domain adaptation at this step can be useful. And just I have several questions and I want to answer them, but yeah, definitely compare thoroughly all the methods, all the foundation models, and the domain adaptation method can be helpful, I think, but I didn't do it yet. I think it's something that I want to try, but
Okay. Well, thank you for your answers to those questions, and thank you for your work, for your work on open source software, for your research work, and thank you very much.
thanks.
Thank you. So now, photo.
Thanks a lot. Okay, so thanks a lot for the presentation and for the thesis. I really enjoyed reading it. So there was a lot of keywords in it, like signal processing, PhD, that remind me my youth as an electrical engineer. So that was pretty nice. So thanks a lot for that. I don't have many questions, or all the good ones are already taken, so I'm left with my bad ones. Okay, so just to be sure about the Gaussian hypothesis. So your point is that it is a better compromise between running time, performance, and overfitting.
Yeah, basically is what I was saying. Yeah.
Okay, cool. So one of my questions is that so in your benchmark on SCADA, indeed, as Martin pointed out, is that there are some data sets that for which domain adaptation seems not to really work at all.
Yeah.
So do you have any intuition? It is because of the data? It is because of the method? It is like Office? Well, Amazon Review doesn't work at all.
Yeah. Yeah, I think yes, some of them was easy. I think like 20 News Group was working good, but it was easy data sets. I think it was, yeah, and I think Office 31 is one used often in the adaptation paper. But I think why it wasn't working is because we tried to validate properly the parameters, and yeah, and I think that's why it was not the best here, because the thing harder. But then yeah, optimal transfer is not working so well on it too. And you,
so your claim for this 41 is that the validation method?
No, I'm not sure, because if optimal transport is working, I think same as scroll, there is not there is no parameters to tune, so it cannot be that exactly. It's maybe like that. The things that we did compared to the paper, that is maybe our validation splits are we split at different levels. So maybe we took also smaller data sets, and maybe it's why it's not working so well. Just thinking of that, I don't have the answer just like that, but I'm thinking maybe we just got too much the data set, so now it's a bit smaller to what they use in the paper, and maybe that's why it was not working. But it's true that this one don't have good results, like a burst computer vision, but it's I'm trying just to remember a bit what we did exactly for this for the pre-processing step. Maybe it's also what we use for the vectorizing of the images, but I think we use the classic ones, so yeah, it should have no impact. But just like that, maybe just the splitting of the data, since we have smaller training sets, maybe that's why. But
okay. So in in one of your conclusion, you were talking about detecting the shift.
Yep.
So this seems so yeah, because now up to now the hypothesis is that we have some data and we make the hypothesis that the data has some shift.
Yeah.
And here your point is to we want to apply DA without knowing the shift, and we want to choose the correct method.
Yeah, that's it. Yeah, I think maybe it's not the best way, but when we look to the real datasets, well, I'll move to the table, but I think when you look at the real datasets, most of the working methods was mapping methods. I think most of the time you have a conditional shift, but I would say that just as intuition, I think you have most of the time conditional shift. That's why mapping methods was working better. But it's only 8 datasets, so you have plenty of other application, and maybe sometimes you just have a target shift or a covariate shift, and maybe just using a reweighting method can help better. But just knowing that can be helpful, I think.
And should we have a method that detects the shift, or DA method that is adapted to the shift? Is your thought on this?
No, I think it's a good question, but when you look at deep learning domain adaptation methods, you can try to do, there is method that try to put more, to weight the source samples, like a kind of reweighting methods, but using also losses that try to reduce the diversity, like in the feature space. And so they are trying to do different things, but when you look at this method, there are different losses, so different hyperparameters to tune. So it's still the same question. Do we want to do everything? And if you're doing everything, you maybe have to adapt it. Like you will have parameters for sure, and the best parameter will differ depending of the application. So I think maybe it's just sometimes having simple methods can help. I'm more like, I think in the side doing simple things, but knowing the data and doing the simplest methods. And if you complexify everything, I'm not for that, but
in some of your results in the paper, in the manuscript, you are, I think if I remember well, there was one you claim that your alignment methods works better for low performing.
yes, yeah, more challenging subjects.
Do you have any intuition on that, on why?
I think it's also maybe it's because there is more gain to have, like just so of course if we're working very badly, you can improve them more. Like it's what we saw if you look just at the result for the first paper. We have like just using Chambon with small data sets, we were just using a CNN on small data sets. We I think improve with March mapping normalization 10%. And then for PhD norm, because we were around I think 60% of accuracy, and for PhD norm we are more close to 80% of accuracy. So of course the gain will be smallest because you cannot improve. We saw that even sleep experts have a maximum accuracy of 80% or something like that. So of course you are like you have a bound, and so the improvement is smaller when you have good subjects. So if you have more challenging subject and low performing subject, you have more gain that you can have. So maybe I think that's why it was working better, because we find the solution to resolve the problem of shifts. So now we have more gain.
Okay, so just my last question or comment is not really technical, but I really like SCADA and the open source work. So yes. This is a really nice. I think this is a really nice tool. Now my question is,
it is a very nice tool, but it is useful only if people adopt it. So is there any plan that, or if you have any thought for increase the user adoption of this kind of tool?
Yeah, it's a good question. I think like something that is missing from SCADA right there is just like most of the domain adaptation user is using deep learning, that maybe not everyone, but a big part. And right now, I think SCADA is not the best to use deep learning methods because we don't have good examples. I think we have some methods, but we need like good examples to use them, like to make it very easy to incorporate in your PyTorch pipelines or anything. And right now, it's not the best thing. So first, what I plan to do just to make it work better with deep learning based methods, and also incorporate maybe test time domain adaptation and multi-source domain adaptation, because like people are doing that often in the new papers. Like the traditional pairwise domain adaptation is there is less paper coming out these days. So I just want to incorporate that, and maybe if we have this more modern methods, we can touch maybe a bigger community. So that is this few steps I want to do it, and maybe then I need just to present it more and be like just make some advertisements on, I don't know, LinkedIn or things like that. But it's not it's a bit hard to do, but I think something that we have to do if we want to be known.
Okay, so thanks a lot, and congratulations for all the work.
Thanks.
Merci.
Thank you. Maybe I have just one question, and then I will give you the floor. Okay. Yes, so yeah, congratulations for your work, your presentation, and your manuscript was really nice. And I agree with everyone. So chapter 1 is really amazing. It was great, and it contained one sentence. I surely remember about conditional shift. You give an example saying that, for example, the phrase rock and roll may be positive in a rock CD review, but negative in a PhD defense report. So the challenge is put rock and roll in your PhD. Okay, this is my challenge. But yeah, I just have one question because there were already many questions. But maybe more general is what is the link with federate learning? I mean, can you incorporate all this or some part of it in federate learning where you have several centers, for example, your hospitals, and they don't share the data. So they only can share the weight of the models. So how can we put domain adaptation in federate learning?
I think just the only difference is just the access of the target labels, because you have, for all the domains, you will have target labels because it's yours, so you can train. But I think it's more like the alignment step. If you have different feature representation between all your hospitals, and maybe you can try to align them before. I'm not sure how they're doing it in the second step when you get all the things, or you update your big models. But maybe using that, maybe you can try to even like do a reweighting and put more weights on maybe on hospitals and representation that is like maybe more general. Maybe you can align everything. I think it's interesting. Like I like federated learning, but I never have had time to find like how can we try to mix the two. But I think, yeah, definitely we can do something.
Yeah, it's a bit like domain adaptation, except that you don't have the real data, so you cannot share the
It's
data.
more test time domain adaptation.
Yeah,
I mean,
it's like a kind of constrained domain adaptation.
Yeah.
You cannot adapt everything.
Yeah, you adapt at the second time. Like it's like using our methods, so month mapping. You have this test time, so you never see at the same time the source domain and the target domain. So I think it's usable for for federated learning. But the only problem that what we at the end remove the test time domain adaptation for PSD norm is that you need to incorporate PSD norm to all the model, and you cannot use any models and then adapt after that. You have to incorporate PSD norm at the train time step. So that's why maybe it's not a test time. It depends how you define the test time domain adaptation field. But it just like if you want to, it depends how you think about it. So if you want to, like everyone is using domain adaptation and so incorporate alignment method, rewriting methods at every steps, or you want the methods that just working at the last step. It depends. I'm not very familiar with federated learning, so I don't want to say something wrong, but
Thank you. So now maybe your advisors, if they want to say something.
FG first. Yeah, but you were the first director before I was.
All right. All right. So first of all, Theo, first, congratulations for all this work. I think we started together before you were actually started your PhD. You were an intern before, and then you signed for a PhD before I kind of shifted domain, if I may say, 2 years ago now. And so you had to deal with kind of these two domains that were kind of trying to steer the boat with you for this PhD with Remy. I think it's the achievement is great. I think I'm super happy to see that you could do open source, which is close to my heart, and good software, and also learn statistics, do a bit of theory, even though the balance might not be super tight. I think it will be good learning experience. I see this as a training. And maybe just to react to see about how do you make this software used, you need to communicate. Just a message to you. You said it. I think it's not because you miss a feature that people don't use it. Never like this. So don't say people don't use it because I need this new feature that's why people don't use this thing. I think you need to just document, communicate. You did it with the PyData or the events. That was a good visibility. And just if you have a bit of time for this software afterwards, communication is probably where you should spend the energy. It's a different skill after theory and coding, and writing a nice introduction is how to communicate scientifically on what you're doing. My last, not really serious question is, how many hours did you take to make these wiggle lines on your slide?
Not so long, because there is a nice tool, but I didn't know it, but my roommate know it. So it's very easy. So it's a collaboration with other people. Team effort, yeah.
Congratulations again, and with you with the second real advisor, officially.
So Theo, so I want to congratulate you. I think you did many wonderful things in this during this PhD over those many years that we worked together. I know you asked Alexandre first to send you an email, not me. So I know I'm the second here, but I'm very happy to have been the second, and then the first again, because
the second will be the first. Was written in a very serious
way. And so it was. I think you did very nice work, and the thing is, I want to congratulate you. So the quality of the manuscript, the quality of the result, and your implication. And I think that's something that we need to say, and that's something we need to take more into account, is that you work for the community. Don't work only for yourself, and that's something that's too rare. And so, I mean, it's with open source and with it's something that here is quite common actually in this team and everything, but still it needs to be noted. And I know that you also had a very nice impact in the team. You organize stuff, and that's also very important. And yeah, as a rule, I had a problem because when I wanted, to push you, to pressure you, every time I tried, you just had a good reason that you were such a good human being. So every time I pushed, I was like the asshole, and that's because you're so nice. And so it's people need to do that because I mean it's a real pleasure actually to work with you. And I'm very happy. And so it's a bit of a revenge because everything you did, about Monge, so it's personal revenge for me. The thing about Monge mapping is that we had a paper with Karim that is an archive, very old, quite old archive now. And we never managed to publish it. People say, oh, it's linear, it's stupid, or, the bounds are not tight enough. And so we never managed to publish it. But then you applied it to EEG and it works beautifully, and you actually made it work by using this convolution, and that's very beautiful interaction between signal processing, optimal transport, and so I really love what we did together. It was a pleasure to work with you. I think we're gonna miss you. So congratulations, Theo. Again.
I think it was hard to have you stressed. I think even today you didn't seem stressed. Right? At this point in your life, you were stressed.
I don't know.
A few deadlines, maybe.
A bit today.
So it was not visible at the.
Okay, yeah. So I don't know what we are doing.
I think we stay here and everybody.
No. We have a room. Yeah, we have a room because
we have a true room and a virtual room.
Yeah. I send you an email for the virtual room.
Nicolas and.
Yeah, Nicolas.
Yeah, we do receive the link. No problem. Nous voilà. J'entends pas par contre. T'entends Romain, toi?
Non, j'entends pas. Ça.
C'est mieux là?
Ah,
Ah
c'est
ouais,
mieux,
c'est
ouais.
beaucoup mieux. Beaucoup
Ok,
mieux.
on va commencer à parler là.
Bon, alors donc le jury a délibéré. On va vous dire nos conclusions en français. Comme ça, tout le monde comprendra mieux que mon anglais, je pense. Donc Théo, le jury a estimé que tu nous avais fait une présentation de tes travaux qui était très claire et très bien illustrée. Et du coup, tu avais fait une très bonne sélection de tes contributions. Tu n'as pas parlé de tout, mais tu avais bien choisi. En parlant des défis de l'adaptation de domaine et qui se concentrent sur les applications dans les biosignaux, en particulier les EEG. Et donc, tes travaux, ils couvrent un large éventail de contributions qui vont des outils méthodologiques liés à l'adaptation de domaine avec du transport optimal et jusqu'aux bibliothèques open source avec des benchmarks. Et donc, le jury a vraiment apprécié cette volonté de partager tes résultats à travers des logiciels libres et surtout ta capacité à mener des expériences numériques approfondies pour une comparaison équitable, faire des différentes méthodes. Et donc, le jury t'a posé plein de questions sur divers aspects, allant des aspects techniques, en particulier sur la validité des hypothèses, en passant par un point de vue plus général sur le domaine de recherche, pas forcément le domaine adapté. Et tu as su discuter de tout ça avec beaucoup d'aisance et montrant le recul que tu as sur ton travail. Et donc, en conclusion, le jury estime que tu nous as présenté une excellente thèse de doctorat et que tu possèdes toutes les compétences et les qualités pour mener à bien une belle carrière de chercheur ou d'enseignant-chercheur en machine learning. Et nous te félicitons, parce qu'en fait, on n'a plus le droit de proposer les félicitations dans le papier qu'on signe, mais nous, on a le droit quand même de te féliciter. Donc, on te félicite. Tu as nos félicitations. Et il nous propose que te soit donc décerné le diplôme de docteur en informatique mathématique de l'Université Paris-Saclay. Voilà, félicitations. Tu dois lire le serment, parce qu'après, il faut que je coche la case. Il a bien lu le serment, il a prêté serment, donc il faudra que tu le lises. Enfin, si tu en es d'accord, c'est un choix. Hein,
si tu veux pas ton diplôme.
Voilà. Et puis, je n'ai pas placé le rock'n'roll, donc voilà, ce serment est un peu je sais pas, ce que le rock'n'roll est à la musique, le serment est à la soutenance de thèse, donc c'est le rock'n'roll de la soutenance de thèse. Voilà, donc on te laisse prêter ça.
Je peux faire la version française.
Ouais, j'ai pas vu ça. En présence de mes pairs, parvenus à l'issue de mon doctorat en informatique mathématique, ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Une phrase. Ouais, bravo, félicitations.
C'est Alex, il a dit il faut communiquer.
Oh il faut que tu viennes montrer au...
Viens montrer la d'émotion.
Ah ouais, ah là, ça communique. Très bien, la casquette, là, c'est très bien.
T'as bien un discours ou pas?
Ouais, en vrai, si ça vous va. Si vous avez encore un peu de minutes devant vous. Avant ou après le.
Bah, peut-être ça dépend si tu veux libérer du jury ou est-ce qu'ils veulent rester.
Ah oui, est-ce que vous voulez écouter les remerciements qui peuvent durer un petit peu de temps, mais...
Oui, bien sûr, bien sûr.
Voilà. Du coup, je fais mon petit discours et puis après on prend une photo. Il faudra que je me rebranche pour. Bon, on va faire ça. Ok, bon.
Remercie.
Voilà, je vais essayer d'être bref, mais il y a quand même beaucoup de gens à remercier. Donc déjà, je remercie déjà tout le jury d'avoir été là, d'avoir lu la thèse, d'avoir pris le temps de faire ça, de me poser des questions intéressantes et d'être là. Donc merci beaucoup et de m'avoir discerné du coup enfin, d'être docteur, quoi, le statut de docteur. Et moi, ça rend quand même pas mal pour moi parce que, je sais pas, enfin, je viens quand même de banlieue populaire. On m'a jamais trop, enfin, dès le collège, on nous disait qu'on formait pas d'ingénieurs ici, qu'on était juste fait pour être ouvrier, quoi. Enfin, voilà, c'est pas forcément le top à dire. Et puis au lycée, on m'a pas beaucoup poussé vers la prépa parce qu'on me disait que ça allait peut-être pas trop marcher pour moi. Mais pourtant, je suis là, donc je suis content. Donc je suis un peu fier quand même d'avoir montré à ma proviseure que c'est possible, quoi. J'aurais pu. Mais bon, moi, je suis pas arrivé là tout seul. Je suis arrivé là aussi grâce à plein de gens. Tout d'abord par ma famille, hein, qui sont pour la plupart ici, sauf mon petit frère, quoi. Mais non, ils m'ont toujours montré que, en fait, ils m'ont jamais mis de pression à faire quelque chose en particulier, mais je pouvais faire tout ce que je voulais. Je savais qu'ils allaient être fiers, quoi que je fasse. Donc ça aide, quoi. Bon, du coup, on est un peu plus détendu quand on sait ça. Que voilà, je savais que j'allais les rendre fiers et je pense que je les ai rendus fiers aujourd'hui, mais je pense que je les aurais rendus fiers en faisant n'importe quoi. Donc merci, merci de m'avoir donné ça et je vous aime beaucoup pour tout ça. Et ensuite, bien sûr, je me suis entouré de très belles personnes tout le long de ma vie, hein, et donc là, on peut le voir ici parce que j'ai plein d'amis qui sont là et qui viennent, les plus vieux amis du lycée, quoi, à la prépa, à l'école, au master, même à Montréal, quoi. Tous mes amis de chaque période de ma vie sont représentés ici, quoi. Donc merci beaucoup d'avoir fait le déplacement et d'avoir pris le RER. Je sais que pour certains, c'était un peu dur là, et j'étais pas trop content de le faire. Donc je merci d'avoir été là, quoi. C'est trop cool. Ensuite, ben, forcément, je vais remercier le labo, un labo vraiment incroyable qui est MIND-INRIA. C'est à la fois dur et facile d'être dans ce labo parce que dur, parce que en fait, vous êtes tous super brillants. Donc, je pense que tout le monde ici, quand on arrive, on se dit, mais qu'est-ce qu'on fait là? Ils sont peut-être si forts. Je devrais pas être là. Genre, je pense que tout le monde a ressenti ça. Et c'est beaucoup plus simple, je pense, d'être impressionné par les autres que par soi-même. Mais, euh, mais si vous êtes impressionné, je sais même peut-être pas, mais si vous êtes impressionné par la thèse, ben, elle est là grâce à vous, en vrai, parce que j'ai appris beaucoup de vous, que ce soit à coder, à faire des maths, à écrire des papiers et tout ça. Mais c'est aussi facile parce que vous êtes brillant, mais aussi un cool, quoi. Et donc, c'est toujours un plaisir de venir là. Et franchement, je vais sûrement louper des moments, mais il y a plein de moments que j'ai eu avec les gens du labo, que ce soit les premiers appels Zoom quand on était en stage ou les manifs que j'ai pu faire avec d'autres personnes, ou des foot, des tennis, des soirées Age of Empire, tout. Je pense que je loupe plein de choses, mais juste tout ça, en fait, ça donne envie de venir au boulot, ça donne envie de bosser, ça donne envie d'aider les autres. Et on n'a pas eu de compétitivité du tout, c'est vraiment que de l'entraide, ce labo-là, et ça donne envie d'être là, et ça m'a donné envie de faire plein de choses avec vous, et je pense que vous l'avez vu. Et c'est grâce à vous, tout ça. Et donc, je me remercie vraiment pour tout ça. Et franchement, je peux que remercier quand même 4 personnes avec qui j'ai fait toute ma thèse. Donc, je remercie forcément Félix pour ta bienveillance, Julie pour ta bonne humeur et ton sourire tous les jours en arrivant dans le labo. Ambroise pour ta gentillesse et aussi tes crêpes qui sont très bonnes. Et Samuel, que je ne vois pas, mais enfin, pour ton sens de l'humour, pour tes petites blagues bien placées, là, ça m'a toujours un plaisir de vous voir et d'arriver au labo avec vous, quoi. Donc merci beaucoup. Et juste un dernier mot forcément pour mes encadrants. Donc Rémi, Alex et Antoine, il ne faut pas l'oublier. Parce que sans Antoine, cette thèse aurait été beaucoup moins rigoureuse, beaucoup moins innovative et moins bien codée, ça c'est sûr. Euh, donc, euh, donc merci beaucoup Antoine d'avoir été là. Enfin, tu as vraiment rendu cette thèse encore meilleure. Donc je te remercie vraiment d'avoir fait tout ça pour moi, quoi. Et je sais que là, tu as choisi de quitter la recherche. Tu aurais été un très bon chercheur, mais j'ai hâte de voir ce que tu vas faire dans la suite. Je suis sûr que tu vas faire de très belles choses. Donc, merci beaucoup. Alex, ben, bon, c'est un peu moins vu, malheureusement. Malheureusement, mais je suis quand même impressionné par la précision de tes conseils. J'ai toujours eu le mot juste dans chacune de nos meetings, de remettre un peu si, de me guider si j'étais un peu perdu, de me remotiver si j'étais un peu moins motivé, de me conseiller même au niveau du code, de l'écriture d'articles ou quoi. Chaque conseil était toujours pertinent et très précis. Je suis assez impressionné par ça et je pense que j'espère que je pourrai être comme ça dans les prochaines supervisions, quoi. Donc, on espère. Et après, je pense que je remercie quand même la personne qui a le plus stressé dans ma thèse, même plus que moi, je pense, donc Rémi. Euh, donc merci beaucoup Rémi. Enfin, ouais, c'est assez différent d'Alex quand même, comme supervision. C'est pas, c'est un peu moins précis, c'est un peu plus dans tous les sens, mais il y a plein de belles choses, quoi. Et moi, tu m'impressionnes beaucoup. Enfin, tu es pour moi un grand chercheur avec des tonnes d'idées et des voies dures à suivre, mais ça va dans tous les sens, c'est top. Et moi, je suis impressionné parce que à la fois, tu es un bon chercheur, mais tu es aussi quelqu'un qui prend vraiment beaucoup de temps pour tes doctorants, qui prend du temps pour ses élèves et faire des bons cours, et aussi du temps pour ta famille. Tu as vraiment un équilibre entre la recherche et ta famille. Et moi, je trouve que c'est assez incroyable. C'est là où je me dis, je peux être chercheur parce que je peux être comme toi, quoi. Enfin, et ça me fait plaisir, quoi. Enfin, c'est vraiment tu seras un modèle pour moi et j'espère un peu arriver au moins un peu comme toi. Et donc, je suis content en soi de terminer cette thèse parce qu'on va perdre un peu ce lien hiérarchique, mais on va pouvoir vraiment devenir amis, quoi. Et ça me fait plaisir. Et, et voilà, je remercie tout le monde, je crois, hein. Enfin, j'espère. Donc, merci à tous et à toutes d'être là. Et voilà. Merci.
OK.
Tu veux que je les remette?
Je ne sais pas si on va réussir à faire une photo.
Ah oui.
Non, mais tu feras un montage.
Demande à ChatGPT.
Ouais.
C'est vrai qu'après, je sais pas comment on met les deux à côté.
Ouais, je pense que ça va être compliqué. On va vous laisser, on va vous libérer. Merci beaucoup.
Merci beaucoup d'avoir été là.
Allez,
Merci.
bravo Théo et merci pour l'invitation.
On n'entend rien du coup. Attends.
Ah, on n'entend pas.
Ah, c'est bon, on vous entend.
Ah,
Ok.
très bien. Je disais bravo à Théo et puis merci pour l'invitation à vous. Bonne fin de journée.
Et merci beaucoup
Merci
à tous les deux.
Merci beaucoup.
Ouais.
Bravo Théo et puis
Salut.
faites-toi bien.
On se voit dans quelques semaines, Romain. Du coup.
Ouais, à très bientôt, ouais. Salut.
Ok.